All right, so 10.3. So in the last section we learned about one way to multiply vectors. We had the dot product. And today we're going to talk about another way that we can multiply vectors. The reason that we're waited until we talked about three-dimensional vectors to talk about cross products is because cross products only work or only are defined for three-dimensional vectors. All right, so if we have vector u is u1, u2, u3, and vector v in component form v1, v2, v3. We get u cross v, and we call it the cross product because we're showing the multiplication with an x cross instead of a dot. Is this thing that looks kind of complicated. U2 v3 minus u3 v2 I hat minus u1 v3 minus u3 v1 k hat, sorry, j hat, plus u1 v2 minus u2 v1 k hat. There's a bunch of stuff going on there.
First one minus something plus the plus. Oh god.
What's that?
It's just like, why is the first one subtracting the second one? And then they're adding the third one. That's weird.
So it turns out that we something that we talked about at the beginning of the semester is going to help us out a lot here. This is equal to a determinant. I hat, j hat, k hat, u1, u2, u3, v1, v2, v3.
Oh, wait. Oh my god, it's a matrix.
This is why I said at the beginning of the semester that we had to learn how to do 3x3 determinants by hand because we need them to do cross products. And remember, to do the determinant, we do I hat times, and we cross out that column and that row, u2 v3 minus u3 v2. And remember, our signs went plus, minus, plus.
Oh my god.
So we have a minus, j hat, u1 times v3 minus u3 times v1, plus k hat, cross out that column and that row, u1 v2, u2 v1. So the cross product is not actually a determinant. The determinant is just a way to help us remember how to do it. It's just convenient to think about it in this form rather than in this form. So if we do this, we get this thing. One important thing to see here is that the cross product is a vector. So the dot product, remember the dot product was a scalar, just a number. We've multiplied the x parts, multiplied the y parts, multiplied the z parts, and added them all together. Cross product is a vector. So what I want to do is do a couple of examples of just calculating a cross product, and then we'll talk about their properties, because the properties are what make them useful and interesting. All right, so let's say that u is the vector I hat plus 2j hat minus k hat, and v is the vector 3i hat minus j hat plus 2k hat. So if we want to do u cross v, we're going to make this determinant. I hat, j hat, k hat. I always write these down because it's very easy to make an arithmetic error or a sign error calculating these. So I'm going to say I hat times. We'll cross out that column and that row. 4 minus 1. Minus, remember our signs go plus, minus, plus. J hat times, cross out that column and that row. 2 minus negative 3. And then plus k hat, cross out that column and that row, and we get negative 1 minus 6. And we simplify this, and we get 3i hat minus 5j hat minus 7k hat. So there's our cross product. Let's look at V cross U. Any guesses what's going to happen here? Well, let's calculate this out. We get I hat times, cross out that column, that row, 1 minus 4 minus j hat times negative 3 minus 2 plus k hat times 6 minus negative 1. And I get negative 3i hat plus 5j hat plus 7k hat. Right, the signs are all different. So we see that U cross V, in this case, is negative V cross U. So cross products do not commute.
Wait, why
You can't change the order.
Why is it negative?
What's that?
Why is the thing negative?
That's just the way it works. When you switch the rows, switch two rows, you change the sign of the determinant.
Okay.
So with cross products, the order matters. So you have to do cross products in the correct order. So they're a little different than numbers that way. So they don't commute. All right, questions on our procedure there? Okay, let's talk about the properties of the cross product. So these first ones are some properties of how we do arithmetic with cross products. Well, we saw U cross V equals negative V cross U. Order matters. U cross V plus W, we can distribute with this kind of multiplication as long as we keep the order the same. So that's going to be U cross V plus U cross W. If we're doing the cross, if U is in front here, it has to stay in front. We have to keep the correct order. A scalar multiple times a cross product is the same as the scalar multiple of one of the vectors crossed with the other, and that's the same as U cross C times V. C is a scalar. any vector crossed with the 0 vector is the same as a 0 vector crossed with any vector is the 0 vector. Any vector crossed with itself is the 0 vector. And then this last one, we'll write it down, then we'll come back to it in a little bit. U dot V cross W equals U cross V dot W. And we call this the box product or the scalar triple product. And we'll talk about why it's called the box product in just a minute. All right, so those are some of the properties of how we do arithmetic with cross products. What's really more interesting about cross products and how they get applied more is the geometry of cross products. So let's talk about that. The geometry of the cross product. The first one, and this is why we have to have 3 dimensions to have cross products. U cross V is orthogonal to both U and V. So what we're saying here, and remember orthogonal means makes a 90-degree angle with, if that's U and V, U cross V is going to make a 90-degree angle with each of those. So both of those angles are 90 degrees. And if we did the cross product in the opposite direction, we would get V cross U. So if we have 2 vectors in the plane, the cross product is perpendicular. So if our 2 vectors are in the screen and we do the cross product comes out of the screen. So that's why we need 3 dimensions to do a cross product.
Oh yeah, because it's 3-dimensional. I was thinking it was 2 vectors.
What?
So, you see we made the right angle sign?
Mhm.
It's that little triangle right there.
It's a right angle that goes.
It's a right angle behind the other right angle.
Oh.
You have to look at it in a new perspective.
This is a 90-degree angle, and that's a 90-degree angle.
Man, that's huge.
So this one important geometrical idea with the cross product. The second one, the magnitude of U cross V is the magnitude of U times the magnitude of V times the sine of the angle between them. So remember we had something like that for the dot product. U dot V was magnitude of U times the magnitude of V times the cosine of the angle between them. So the cross product has to do with the sine of the angle between them. So another word that you use, so orthogonal is the word we use for perpendicular when we're talking about vectors. If you talk about a vector in relation to a surface, the word you use for perpendicular is normal. So do you know why the chicken crossed the road?
Because it was hungry.
No. To be normal. Chicken crossed the road. to be normal?
What's the road?
Chicken across the road is normal.
Oh.
And with this one, do you know what you get when you cross an elephant and a banana?
Hair.
Elephant, banana, sine theta.
I'm sorry, where are you getting an elephant from?
Elephant, banana, elephant, banana, sine theta.
What's the function?
What do you get when you cross an elephant and a banana? Well, the cross product of an elephant and banana is elephant, banana, sine theta.
What is that supposed to be?
The magnitude of elephant times the magnitude of banana.
Right. It's technically it's a magnitude of elephant times the magnitude of banana times the sine of theta. That's my favorite vector joke. All right. U cross V is 0
Oh, wait, that's 0?
if and only if U and V are parallel. What's another way that we say that two vectors are parallel? They don't necessarily have to be collinear.
What about this kind of scalar?
The scalar multiple of each other. So the cross product being 0 gives us a way to decide or figure out or know the vectors are parallel. The dot product being 0 gives us a way to decide or know if two vectors are, what does dot product equals 0? What does that tell us? They're orthogonal. So the cross product has to do with being 0 has to do with parallel vectors. The dot product being 0 has to do with orthogonal vectors. And finally, the magnitude. This one is the one that ends up being applied in all kinds of different ways. U cross V is the area of the parallelogram. With U and V as adjacent sides. So what we're saying here is if we have two vectors like so, that's U and V. If we extend this here and make another vector same length as U there, and we make another vector the same length as V there, the area of this parallelogram equals the magnitude of U cross V. So the fact that the cross product gives us an area turns out to be extremely useful. So the cross product gives us an area of a shape in the plane. When we talked when we were talking about matrices, we talked about applications of the determinant, and we did problems that had to do with if we knew the vertices of a triangle, and we could use a determinant to find the area of that triangle. And we had a 1/2 in there. Basically what we were doing was finding the cross product of those two vectors and cutting it in half to find the area of a triangle rather than the area of a parallelogram. This property, that the cross product is an area, turns out to be one of the really important ones. And I said we'd go back to talk about that scalar triple product or that dot product. The reason we call this the box product is this gives us the volume of the solid with U, V, and W as adjacent sides.
Oh.
So the volume of a box.
Whoa, that was basically X, Y, Z.
So if we if we added another vector here coming out of the screen, and we turned this into a box, that scalar triple product or that box product would give us the volume of that box. So that's why we call it the box product. All right, let me look at an example. So a very typical kind of problem that you have to do with cross products is find a unit vector orthogonal to both u equals 1, -2, -3, and v is 0, 4, -5. Well, a vector orthogonal to both u cross v is orthogonal to both. And we want a unit vector in that direction. So to get a unit vector, we're going to divide u cross v by its magnitude. So the cross product gives us a vector that's orthogonal to both of those, and we divide it by its magnitude to get a unit vector. So let's find u cross v. U cross v, get this determinant, I hat j hat k hat, 1, -2, -3, 0, 4, 5. I hat times -10 minus -12 minus j hat times 5 minus 0. Yeah? Oh, is it -5? Negative, so let's see, where did I mess up? This should be positive 10 minus -12. J hat should be -5. Is that right? Yes? Minus 0 plus k hat. This is why I always write it down, because it's easy to make those kinds of mistakes. K hat times 4 minus 0. So we get 22 I hat plus 5 j hat plus 4 k hat. So this is orthogonal to both. How could we tell, or how could we just check to make sure we did this correctly? How could we check if this was orthogonal to both of those vectors? Do the dot product, and if it comes out to be 0, they'd be orthogonal. Well, let's look at this one really quickly. Since we have a 0 I hat, we get 4 times 5 plus -5 times 4 is 0. All right, we want a unit vector. The magnitude of u cross v is the square root of 22 squared plus 5 squared plus 4 squared, which is the square root of 525. So our unit vector is 1 over the square root of 525 times the vector 22, 5, 4. And now you've shown me enough that you know how to, more or less know how to do that. Almost. All right, this next one, I don't want to go through all the work, but I want to talk about how we would set this up. Let's find the area. Parallelogram with vertices. P is 1, 1, 1. Q is 2, 3, negative 1. R is negative 1, negative 2, 2. And S, which is 0, 0, 0. So that they give us the vertices of this parallelogram. Now, from geometry, you might remember that the naming convention for polygons is to start at one vertex and go in order, either clockwise or counterclockwise. So this could be P, Q, R, S. All right, so how are we going to find the area of this parallelogram?
The equation that you gave us.
Well, we need some vectors, don't we?
No.
Can't we turn that into a vector? Vector PQ
Whoa.
by doing terminal minus initial?
Yeah, that's awesome.
And we can do this vector PS, terminal minus initial.
Yeah, then we can do cross product, and that gives us the area.
Right, our area is the magnitude of PQ cross PS. What if the problem then asked, is it a rectangle? Now it does.
You have to find it at 90 degrees.
Right, we need to figure out if this angle is 90 degrees. How would we do that? Dot product. If we do the dot product, PQ dot PS,
Over the magnitudes.
and we don't even have to use the magnitude. If that's a 90-degree angle, what does this come out to?
0.
So what we're interested in is PQ dot PS equal to 0? If it is, then it's a rectangle. If it is not, then it's not a rectangle.
That's so crazy.
Oh, is it like
All right, questions? Okay.